Okay, so let me share my screen and we're going to talk about our next section here. Okay, not much up there to see quite yet, aside from the fact that we are going to be talking this afternoon about section 7.5, which is all about solving equations, specifically rational equations. Get my pen all queued up here. Remember that anything rational is dealing with a fraction. And you can see within the word rational is the word ratio, which means a fraction. But for us specifically, it's a kind of fraction and I should add a word here. It's a fraction that is often going to contain variables. In fact, we could say usually it's going to contain variables. So informally, I usually tell people it's a fraction with x's in it. We did talk about the fact that something like 2/3 is still rational because you could look at it as or maybe, and so on. So you could have an x to the 0 power in there, and x to a power contained in a fraction means that that fraction is rational. But most of the time, we see the x's. They're there loud and clear. We don't have to think too hard. They're going to be right in front of us. So just to review on what rational means, and we have not yet placed rationals inside of equations. So as a review, when we have to solve an equation, so this is something we do pretty often in algebra, but in between the sections where we have to solve equations, there's often a lot of sections where we merely simplify. So stuff like exponent rules, factoring, that's often just taking one expression, simplifying it out so it looks like something else. But solving equations, this is where we work down to where x equals either a number or maybe more than one number, depending on the scenario. So just as a review, that's what we're aiming at. We want x, or it could be y or any other letter, whatever they give us. We want that to equal some kind of number, and then we know we're done. Now, for rational equations, there is going to be an extra step. I feel like there's always some bad news anytime we start a new section. Even after you get to the point where you know that x equals these numbers, there's a step beyond that. So this is an extra step at the very end of the problem. And I'm going to write what that extra step is, and this won't make any sense to you right now. Particularly because it involves a big word. At the very last step, you are going to have to check for something that's called extraneous solutions. And if and only if you find any, you're going to throw them out. They are not included in your answer. Now, the part that I would have you pay attention to in the word extraneous is this part right here, extra. Basically, you're going to be looking for some extra solutions that don't actually solve the problem. Okay, I am going to have to pause my recording. So hopefully this is going to be successful. This is the first time I've paused the recording and come back. So if it all goes away, at least I'm not very far in. All right, let's see if that worked. It appears my recording is back, so we'll just pick up right where we were. Okay, so we're going to be looking for something mysterious called extraneous solutions. And if we find any, we're going to throw them out. And the best way to get into this is just to do it. Just dive right in. So first practice problem on page 410. So there's a rational expression. Remember, this is also a rational expression, 3/2. And there is another rational expression. And we want to solve this down until we have x equals 11. Okay, so the way to do this is, unfortunately perhaps, although it's not too bad in this particular problem, but we have to identify the LCD, because our goal is going to be here. I'm going to put that. We're going to clear the fractions first. This is one of those times when we revert back to that process. If there's any fractions, we want to get rid of them. And in the world of rational things, there's always going to be a fraction, because that's by definition what something rational is. Okay. So we want to clear the fractions first. We're going to use the LCD to do that. So for us, in this problem, the LCD is not too difficult to find. We're looking for the smallest number, or the smallest expression that all three of our denominators will divide into. And as a matter of fact, one of those three denominators actually is the LCD. It's 8, because 2 divides evenly into 8, 4 divides evenly into 8, and 8, of course, divides evenly into itself. So the LCD is 8, and what we're going to do with it is we're going to multiply the whole problem through by that LCD. Specifically because that is what will enable us to clear those fractions. Okay, so here we go. Let me not tamper with the original problem. Let me come down here. Okay, and then we'll grab our 8 and we'll multiply through. So every single part of that problem, it's an 8. And if you're interested in being extra technical, it's an 8 over 1. So if you feel like you need to see that, most people eventually think that clutters it up. But if you need to see it, you can. It's an 8 over 1. Okay. And then we're going to reduce. We're going to reduce each and every one of these expressions with that 8. Okay. So 4 can reduce into 8 with a 2. 2 can reduce into 8 with a 4. And then the 8s themselves here at the end, those can cancel away. Okay. Now, because this is the first problem, and it maybe has been a while since we have had to clear fractions, let me put in a middle step here. So we have 5x now times 2 minus 3 times 4 equals 7x, really times 1, but we probably need to write that. So what we will do, multiply that 5x and that 2, we get 10x. And notice we've now arrived at something that is extremely basic algebra. We're trying to isolate x, and just my personal preference, we're going to put the x's on the left, the numbers that are not attached to x's on the right. So this 7x, I will subtract it from the 10x, I'll get 3x. This 12, I will add to the other side, like that. And then eventually I'll get x equals 4. Now, I haven't yet told you what an extraneous solution is. So is now the time that we need to do this? Do we need to investigate whether 4 is an extraneous solution? No, we don't. And I'm simply going to state we don't need to check at this point. And there's a reason for that, and I'll state the reason. Just kind of warm us up to these extraneous solutions without getting into too much detail all at once. We don't need to check for extraneous solutions because in the original problem, there were no variables. So for us, there were no x's in a denominator. So just bear that in mind. If there had been x's down below the fraction line, so if there had been some x's down here with the 4, the 2, or the 8, then there would have been a possibility that maybe an extraneous solution or two would have revealed itself. But for us in this problem, okay, now here, practice problem 2. And I'm sure it'll come as no surprise based on what I've just said that the next thing the book does to us is introduce x's in the denominator. So here we've got 3 separate expressions that go together to make up this equation. And 2 of the 3 denominators involved contain x's. Now, all we would need to kind of send warning bells going off in our mind would be for one of those denominators to have an x in it. If at least one of them has an x, we're going to have to think about extraneous solutions. Okay, so now there are x's in denominators. So we will have to be on the lookout for those extraneous solutions. And so at long last, I'm going to go ahead and state those are x values that appear to be solutions to the equation, but when we look closely, they make a denominator equal 0. And that's bad. In algebra, we do not want a denominator to ever equal 0. Now, what I would advise, just to avoid getting enmeshed in the problem and forgetting all about extraneous solutions, is to set yourself up for success right from the beginning. So figure out what x values would be extraneous before you even get started. Now, this is not hard and fast. This is just me trying to save you some grief, because I just know from experience that anything that requires us to go and check stuff at the end of a problem, usually that's the thing we're going to forget to do. We get so involved in the problem itself and we forget that, hey, there's another 2 or 3 steps after that. And so in order to do this, look at your original denominators and just set them to 0. Find out what those extra solutions would look like. So we have x. Let me go back to black. And I'm kind of line this up. We have x equal to 0, we have 5x equal to 0, and we have 5 equal to 0. So we're just trying to set them all equal to 0. Now, 5 cannot be 0. So without further ado, that doesn't make any sense. Let's cross that out. X equals 0. This is an extraneous solution possibility. We don't know if this problem will yield any x equals 0s, but if it does, we're going to have to throw them out. Now, 5x equal to 0, just a quick step here, let me divide away that 5. X equals 0 again, basically same thing. I just revealed the same extraneous solution possibility twice. Okay, so we're on the lookout for x equals 0. If that comes out of the woodwork at the end of the problem, we know that we're going to throw it out. Okay, so now is the point where we're going to ask ourselves, what is our LCD? And the LCD here has to involve the letter x, the variable x. It also has to involve the number 5. If you look at that 5x carefully, that is actually my LCD because, well, 5x as a term divides into itself. 5 divides into 5x, and x divides into 5x. Okay, I have to pause this again since that went so well before. I'll be right back. All right, back to recording. Somehow I canceled my shared screen. Okay, so our LCD is 5x, so that's the quantity that I am going to now take and distribute very carefully through my entire equation. Now, when I do that, notice here, just to form good habits, that x plus 9, if anything is left to distribute through that x plus 9, it needs to go through both parts, the x and the 9. I don't think that will happen here. Let me get yet another color for the canceling color. Starting to get more and more complex problems here. So the x's cancel in the first term. The entire 5x cancels with the 5x in the second term. And the 5's cancel in the third term. Okay. And what's left, I'm even going to preserve my color coding here. Just, well, for the most part, just to keep us from falling into too many pitfalls in our first couple of examples. 2 times x. Okay, so we're down to one line. It looks a little bit messy, but in the next step, I'll clean that up, make it beautiful instead of messy. So here we've got 30. I am keeping those parentheses because the negative needs to affect both the x and the 9, which is what I'll do in the very following step. We'll have negative x minus 9, 2x. Okay, so 30 minus 9, my like terms on the left-hand side. 30 minus 9, that's going to be 21, and I hear my child kind of falling apart at the seams in the next room, so I'm going to have to go deal with him in a minute. I am going to follow through with my preference and keep the x's on the left with the numbers on the right. So my 2x, I'm going to subtract it and give myself negative 3x. My 21, I'm going to subtract it, temporarily create kind of an ugly setup here. Okay. Pause the recording. I shall return. Not pause the share. Pause the. Okay. Okay. Now we got x equals 7. This is a possible solution. This could be the answer to our problem. Our problem. Pardon the sound of a toddler crying in the background. About the time that I decided I was going to stockpile these recordings for you guys, it was like all hell broke loose in my life. And yeah, so I apologize for the quality of some of these recordings because we're dealing with a lot of stuff in our life right now. But isn't everybody? This is a possible solution, but we need to check if it's extraneous. In case you're wondering, he's freaking out because he keeps thinking the trash man. He's supposed to be napping. He keeps thinking he hears the trash man. I will let him get up and look at the trash man, but you can hear the trash man for like miles before you see him because he's so loud. So we have an overtired toddler, and it's just a bad combination. So remember that our only possibility for extraneous solutions was x equals 0. So this is where trying that at the beginning, checking that at the beginning of the problem, just kind of establishing that at the beginning of the problem is going to make it a lot easier on us going forward. So x equals 7 is not x equals 0. So we can officially keep x equals 7. Okay, and just go ahead and write that down there. That is our answer. Okay, let me go see if I can calm his little self down. All right, let's resume the recording for another couple minutes here. Now I went ahead and wrote out the next problem for us, and we're going to solve this. And the very first thing I want us to do before we even think about what's my LCD, I want us to check for possible extraneous solutions by setting our denominators equal to 0. Okay. So really, well, we get the same thing twice. So what that means is -3 is a possible extraneous solution. The reason I keep saying possible is, of course, we don't yet know if we're going to turn up any x equals -3s. But if we do, it's worth noting right at the beginning of the problem that we would have to throw them right back. So with that in mind, let's continue on and go to the step where I start thinking about the LCD. So the LCD here. And really, this is a point where I have to introduce a couple of things, parentheses, and a first power here. So we have matching items. We have x plus 3 to the first, x plus 3 to the first. So our choice for the LCD is basically x plus 3 to the first, which of course is x plus 3. So what we're going to do, I'll rewrite the problem for us since we have all of this pink writing in between here, and we'll see where we can go from here. So x minus 5 over x plus 3. And what I'm going to do, keep that. I'm going to multiply by my x plus 3 to both parts. Now, when I do that, I just like to be extra safe. I'm just protecting like everything that I possibly can in parentheses. Sometimes that turns out to have been more work than we needed, but it's never a waste of time because when you need those parentheses, you really need. So the canceling here, because the LCD was found under both factors, the canceling is very simple, doesn't leave much behind. So we get x minus 5 equals 2 times x minus 1. And the parentheses around the x minus 5 at this point, since there's nothing sitting out front or back behind to multiply through the x minus 5, is the parentheses are unnecessary. So x minus 5 can just sit like that. On the right-hand side, though, the 2 will have to distribute. So we get 2x minus 2. Okay, and then shuffling everything around like we like to, I'm going to subtract 2x from both sides and leave myself a negative 1x. I'm going to add 5 to both sides. That gives me a positive 3. X equals negative 3 is a possible solution. Every time I write down x equals something, it's only possible the first time I write it down. And what kind of phrasing did I use? I need to check if it's extraneous. It is. So by what we did just a couple of minutes ago, x equals negative 3 was our only possibility for an extraneous solution. We've gotten it. So we have to throw out x equals negative 3. And that's unfortunate because negative 3 was the only possible solution this problem gave us. So we just threw out our only possible solution. So that means there's no solution. Sometimes there might be 2 possible solutions and you only have to throw one out. And that's nice because you have something to show for your work. But in this case, it's gone. There was our one and only chance and it's gone. So we write no solution. All right, what was that? Practice problem 3. So I get to flip the page to practice problem 4. And we're told to solve this. Every denominator has got an x in there somewhere. So that'll be fun. Everything, every denominator is going to give us some possibility for an extraneous solution. And so I am just going to go through and put them all equal to 0, but I notice that this is really the same as what was under the first denominator. So I don't need to make more work for myself if I recognize that. Go ahead and avoid doing the same thing twice. So I get x equals positive 1 over 5 and x equals 0 as my possible extraneous solutions. So now I've got 2 things to watch for. And then I'll go about my business and eventually I'll return to those possible extraneous solutions and see if any of them actually turn up in the algebra. Okay, now 5x minus 1, I am going to, I'll do that in a minute so I don't have to switch back and forth with my colors. Let me just emphasize again and again 5x minus 1 is one thing, and it's to the first power. And I just mentioned that because if one of these were ever like to the second power, that would complicate my LCD. My LCD would have to reflect that. As it stands, when I'm thinking about putting together my LCD, the pieces that I have at my disposal are 5x minus 1 and x. This 5x minus 1 over here is just a repetition. It's just a twin of the first one. So looks like here I am simply going to multiply together, just kind of smash them together. Or perhaps more traditionally, put the x out front. Either way you want to do it. That's my LCD. So I don't have to worry about, because it's downright illegal, picking apart my 5x minus 1. It is one thing, and the x is one other thing. X will not divide evenly into 5x minus 1. So I have to take them as two distinct pieces, and I think it's safe for me to go ahead and distribute my LCD here. I don't think that will create too much of a mess for us. Okay, so there it is, LCD, 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 3 separate times. And if I've done my work right, each and every one of these original denominators should disappear as it cancels into the LCD. And we'll see what we have left behind. Okay, so 5x times x. And I just feel that keeping the color coding going, maybe because there's been so much disruption over here at my end, I feel like the flow of the technique we're learning hasn't happened yet because I've been getting up and down and up and down. The trash man has come now, so I'm hopeful that peace will return, because if ever a child needed sleep and nap time, it's my child today. He has reverted back to newborn sleep patterns. So, okay, here we go. So 5x times x plus 1 times 5x minus 1 equals 1 times x. So there I am on one line, finally, but I could clean this up a little bit more. No more fractions. 5x squared plus 1 times 5x minus 1 is too trivial to keep writing it like that, so I can remove the parentheses from my 5x minus 1. Like this. Now, here's a case, notice that x squared. So what I have been able to do in the previous few examples is put the x's on the left and the numbers on the right. This problem is going to break that rule because I don't just simply have x's. I have an x squared. Anytime you see an x squared, the good possibility you're going to have to factor this. So this is like chapter 6.7, which was solving equations by factoring. So that was where we had to create a 0 on the right, move everything else over to the left, and factor it. So what we're going to get is 5x squared plus, looks like eventually a 4x minus 1 equals 0. So this is right out of 6.8. So the bad news for us is any kind of solving equation is fair game. We were doing very basic solving equations where the highest power of x that you ever have to worry about is 1. That's what we were doing earlier today. But now we've got an x squared. And so in descending order here, this looks like something that we could do the AC method on. I'm going to state there is no DCF besides 1 plus. So we don't have to worry about that. There are 3 terms, so as a factor review, 3 terms leads us straight into an attempt with the AC method. May not work, but I can pretty much guarantee you it will at this point in our lives, because factoring is all we've got. If this thing doesn't factor, we can't complete the problem. Later on, the book will teach us, before the end of Algebra 2, what to do if something doesn't factor. But for right now, we pretty much know it's going to factor. So 5 times -1 is -5. Thinking carefully about what would multiply to be a -5, but then also add to be a +4, it looks like -1 times 5. So I'm past the point where I write out the 2 separate lists of possibilities. This time I'm more focused. I know I'm trying to add to be a positive, so I set up my pair of factors so the larger of the 2 of them is positive. And then, just as luck would have it, the very first pair of factors I try, starting at 1, normally we go from 1 to 2 to 3 to 4 to 5 if possible. Starting at 1, very first pair of factors gets me 5x squared stays as is, -1 stays as is. All of this is set equal to 0. We're trying to solve an equation here. And then I get -1x plus 5x. And of course, the AC method, if it works, always leads me into a 4-term polynomial, which should factor by grouping if all goes well. So out comes a GCF. The first 2 terms, the last 2 terms don't appear to have a GCF, but that means that I have to put a 1 down there. This is the only time that we have found where 1 is important and not just trivial. So let's see, 5x minus 1, 5x minus 1, matching terms, we're good to go. So here now is my factored polynomial set equal to 0, which means I can investigate each of these factors separately. What if the first factor is set equal to 0? What if the second factor is equal to 0? These should give me 2 possible solutions, but then I'll have to check them against my extraneous solution possibility. So these guys are possible solutions. We could end up keeping one or both or neither. Are they extraneous? I'm feeling like one of them is. Let me zoom up to the top here. X equals 0 and x equals positive 1/5. So I don't have a 0, but I do have a positive 1/5. So x equals 1/5 is extraneous, so throw it out. So I'm way too excited about that. So x equals -1 makes it through the process of checking for extraneous solutions, and we get to keep it. So it is our one and only solution. So this is a perfect example of what I was talking about a minute ago. We got 2 that we thought were answers. One of them would make a denominator 0, so we throw it out. The other one's completely safe in any of the denominators, so we're going to keep it. Okay, now I think we are finally at the point here, last 2 examples, where we have to worry about factoring. Now, you might think, well, we just factored in that last problem, but that kind of a situation is not really what I mean. Here's what I mean. the original problem, for the first time, contains an unfactored formula. There it is, x squared minus 4. Now, I'm going to go ahead and, before we even talk about that, I can write this out a little bit neater. Here's the minus sign right here. It is worth doing this at the very beginning. That negative applies to the entire 5 plus 2x. That may become significant at some point in the problem. So we're going to go ahead and put those in. The next thing that we need to talk about is that x squared minus 4, that needs factoring. Now, it doesn't need the AC method. We can't do that. X squared minus 4 is the same thing as x squared minus 2 squared. So if you're remembering back, that's like a squared minus b squared. One of those formulas that you just flat out have to memorize. There is no method per se that you could use on this. So x minus 2, x plus 2. That's my factored form. So I'm going to rewrite this whole problem. Just really make it look like I want it to look before I get started on any of the serious business here. Okay, so we've got that. Here's what we're looking at now. Extraneous solution time. Let's go ahead and set all 3 of these denominators equal to 0 and see what they give us. So we'll set this equal to 0. This is why we needed, or one of the many reasons we needed that middle denominator factor. Now, if you're paying attention here, just really closely to what's going on, the middle denominator actually includes the other 2 denominators. So either way you want to look at it, you've got a lot of repetition. Bottom line, x equals 2 and x equals negative 2 are the possible extraneous solutions. So I didn't technically set the middle equal to 0 because both pieces of the middle denominator are already covered. Or you could do it the other way. You could just go ahead and put the middle equal to 0 and not set the first and the third denominators equal to 0 because they're already covered by that middle. So one way or the other. The possible extraneous solutions, plus or minus 2, that's what we have to look for. Now, off the side here, to avoid rewriting that again, the LCD. Now, again, we've got this to the first power, first power, everybody's to the first power. I could probably stop writing that. The only way to cover x minus 2 to the first power, x plus 2 to the first power, and x minus 2, x plus 2, is really to use that middle denominator as my LCD. It is the smallest thing into which all 3 of these original denominators could divide. There are larger, more complex common denominators that they could fit into, but we want the smallest thing, and it's sitting right there in front of us. So x minus 2 would cancel with this, x plus 2 would cancel with this, and x minus 2, x plus 2, of course, would cancel with itself. So here I will distribute So we can see that LCD 3 separate times, one for each of the terms that make up our problem. And this is where the rubber meets the road. If we've done everything correctly, then the canceling should go really well, and we should have no more denominators in the whole problem. Okay, so now let's see here. I've got 2 times x plus 2. Okay, so far so good. That was left. I've got minus, and then in parentheses, 5 plus 2x. And I believe here, there should be nothing to the right. Yeah, everything canceled out. And then over here, past the equal sign, I've got x times x minus 2. Okay. One nice line with no denominators. Just a little bit of algebra ahead of us before we can start getting some possible solutions. So I'm going to distribute my 2. I'm going to distribute my negative. And I will distribute my x. Ah, unfortunate. I create an x squared. I don't really want to do that, but we'll deal with it. Okay, so on the left-hand side of the equation, my like terms of 2x and negative 2x, they zero each other out. They're gone. They eliminate each other. And then 4 minus 5 is just a negative 1. No like terms on the right-hand side. Okay, now, as I mentioned earlier, we typically like everything on the left, and then we're going to create a 0 on the right. So as I move my x squared across the equal sign, it becomes negative. As I move my negative 2x across the equal sign, it becomes positive. I already had a minus 1. Now here's the part where you can get clever and creative. Factoring when you have a minus 1 there is not fun. Let me treat that minus 1, even though we never really, or rarely, I should say, we rarely pay any attention to a 1, some kind of 1 as a GCF. Let me treat that negative 1 as a GCF. Let me get that. It changes the signs all the way across. And what's left inside here, the positive x squared minus 2x plus 1, that's a lot nicer factor, particularly because we get to use our factoring shortcut. I think that's going to be minus 1, yeah, because those are the 2 numbers that would multiply back to be a positive 1, and that would add back to be a negative 2. And the repetition there, hopefully by this point, you can kind of see I don't need to set them to 0 independently. I can just do it one time. Additionally, I don't need to set negative 1 to 0 because that's meaningless. One number cannot equal another number like that, unless we're talking about reducing fractions or something where 1/2 and 2/4 are the same thing. But 2 integers can't equal each other. Okay, this is a possible solution. Is it extraneous? Check back up at the top. No, only 2 and negative 2. So that means x equals 1. That's our answer. We have one possible solution. We get to keep it. We're good to go. Okay. For last of probably most complicated of our practice problems. Over on page 13, or 413. This has got z's instead of x's. I really don't like writing z's because they keep coming out looking like 2's. Okay, here's what we've got now. We've got some work to do. Before we can think about trying to figure out what our extraneous solutions would be, we have got two things that need factoring. Unfortunate as that seems. Now, the one that I just wrote needs factoring underneath, the right-hand fraction. That factors very quickly because we're just going to pull out a GCF of z. Okay, we're done deal. The other one, there is not a GCF that is other than 1. We're going to have to do the AC method. There we go, AC method here. So 2 times -6, -12. And I'm going to be clever here. I'm just going to dive right to the 2 factors. As you do more and more of these, you'll probably find yourself doing that as well. You don't have to write out a complete list. Just go to the correct 2 factors. Now, if you're coming up empty, if you feel like you can't figure out what those are, then by all means, revert back to the long and thorough way. That's what it's there for, is to help us when we feel stuck. 3z minus 4z. Okay, last 2 terms are led by a negative, so I have to pull it out along with my, apparently, 2. So we get plus, right. And somehow I switched back to the black marker when I didn't want to, but it's not the end of the world. Okay, so I'm going to rewrite this problem. So now we have z over a nice factored polynomial. We have our middle term, which has not changed. It didn't have any factoring. And then we have our factored right-hand denominator. Okay. So here's the problem in its factored form. Now let's go ahead and check for extraneous solutions. So we're going to just recopy our denominators set equal to 0. Okay, and of course that means in the case where there are multiple pieces per denominator because of factoring, we have to do that. We have to split apart, consider them separately. So z equals 0, so that was quick and easy, just divide out 3. And then I think this is already done as part of one or the other denominators. So z equals 3 halves, z equals 2. so much going on here. I'm going to circle, circle, circle. All of that is possible extraneous solutions. Okay, now, because this problem is so messy, I'm going to write it out one more time. I tried to avoid doing that in the last problem, but this one, because it's the final one, just a special problem. So I have to start questioning what's the LCD. Pieces that have to go into this LCD. I see that 3. There has to be a 3 in my LCD for that 3 to cancel it. I see some z to the firsts. And remember, the denominators have to cancel with the LCD individually. So the fact that there are 2z to the firsts, I just write that one time. There are some z minus 2 to the firsts. There is a 2z plus 3 to the first. So I have to have a 2z plus 3 in my LCD for that little guy to cancel with. And then I have to have a z minus 2 so that both of my z minus 2's, as they individually interact with the LCD. So there's the LCD. Just kind of make sure that each and every denominator is represented. Could you take your finger, block out certain parts, and be left with each individual denominator? Is the question that you're going to ask yourself. And I can do that on a whiteboard. I can't do it currently. Let me multiply out my LCD. So I distribute it, and it is so long that it doesn't want to fit nicely anywhere I put it. So cancel every single thing that we can. This is too much like work. Okay, so we have that z times. And I'm just going to stick with the color coding to the bitter end. These problems are intense enough. Anything I can do to make it seem a little bit less intense, I'm going to do it. All right, so there we go. Oh, it's so ugly. Okay. So z times 3z. That's going to give me a 3z squared. Now this negative 1, I'm going to leave it, and then I'm going to just distribute out these two polynomials. Now, I have to leave them in a set of parentheses so that that negative 1 can come along and change all their signs. So 2z times z, 2z squared. 2z times negative 2, so minus 4z. 3 times z, 3 times negative 2. So there I go. Over here on the right, all I'm going to do for a first step in the cleanup, 2 times 3 is 6. There we go. And it's up to you, but I'm going to hold my negative 1 out front for one more step so that I can clean up this interior polynomial. A couple of like terms, every little bit helps. On the right, I will finally dive into my distributive property. So much algebra. I'm trying not to think about all the different ways I could mess this up before I even wonder about solving for Z. All right, the right-hand side cleaned up as it can get. The left-hand side, though, I could bring 3 minus 2 is 1 Z squared. Now, I'm going to drag everything over to the left-hand side. Looks like that will leave me with Z squared minus 11Z minus, what is that, 12? Another chapter 6 factoring. What are my magic numbers? 12 and 1. Okay, if the 12 is negative and the 1 is positive, they will multiply to be a minus 12, and they'll add to be a minus 11. So, getting closer and closer. Okay, so positive 12 and negative 1, those are my possible solutions, possible answers. And I don't even begin to remember the start of this problem. Are they extraneous? So I scroll up. All right, 0, 2, and negative 3 halves. 0, 2, negative 3 halves. No. Great. So I get to keep both 12 and negative 1 as my true solutions. And the book might do something like that. Bring back the solution set notation. That is totally up to you if you want to do that. I am happy with the way I wrote it there. Okay, so that brings us to the end of 7.5. Let me finish this recording and get it posted to YouTube. I'm not going to make any wild statements about, I wanted to finish chapter 7, the recordings this week, but we'll see. We'll see. Okay, so very carefully here, I'm going to stop the recording.